Okay, when the video cut off last time, note we were here. We had made a carbon-carbon single bond because this carbon had 4 electrons around it. This carbon had 4 electrons around it, 4 valence electrons. Each hydrogen had 1 valence electron. And when we paired this carbon valence electron with this hydrogen one, we formed this bond. These two form this bond all the way around the molecule, and that gave this carbon having 1 extra valence electron, this one having an extra. We've made a bond between those two. And we know the octet rule was satisfied. Each carbon has 4 electrons around it, 4 bonding pairs in this case. And each hydrogen has 2 electrons around it. Then we looked at this molecule, H2CCH2. We're looking at its valence electrons, and we note that after we form the bonds between the carbon and the 2 hydrogens, this carbon still has 2 extra valence electrons, so does this, but we need... So let's form a bond right here, but take those 2 electrons, form a bond. And when we do that, note this carbon has 1, 2, 3, 4, 5, 6, 7 electrons, as this one does too. It does not have its octet. The carbons still don't have their octet, so let's form a bond here. And if we draw this molecule out as we should, we find we get the 2 hydrogens on this carbon. This carbon is double bonded to the next carbon, and it has its 2 hydrogens on it. And note, when we count our electrons, this carbon has 1, 2, 3, 4, 5, 6, 7, 8. 4 electrons from the double bond. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. Recall, bonding electrons get counted for both carbons. So these 4 electrons get counted when we're looking at the octet of this carbon. They also get counted when we're looking at the octet of that carbon. All right, HCCH. Let's look at that. We know hydrogen has its 1 electron. The carbon has its 4. The next carbon has its 4. And the hydrogen has its 1 electron. At this point, you can probably see, okay, I see what's going to happen here. First thing, yeah, we're going to form the bond between the carbons and hydrogens there. No problems. And can we see we're going to form a triple bond here to get our octet. And we will end up with HC triple bond CH. And when we count the electrons around the carbons, look at this carbon, 1, 2, 3, 4, 5, 6, 7, 8. All 6 of these electrons plus these 2 give this carbon its octet. And those 6 electrons get counted for that carbon too. This brings us to our next little item to stick in your heads: bond strength, bond length. Shorter bonds are stronger. It turns out that if we look at the carbon-carbon bonds here, here's a carbon-carbon single bond, here's a carbon-carbon double bond, here's a carbon-carbon triple bond. The more bonds you have between 2 atoms, the stronger that bond is. Also, the more bonds you have between 2 atoms, the shorter that bond is. So what we see here is, of these 3 carbon-carbon bonds, the carbon-carbon single bond is the longest, and of these 3 it is the weakest. Carbon-carbon double bond is in the middle. The carbon-carbon triple bond is the shortest of these 3. And it is the strongest of these 3. Something to note, very important: a carbon-carbon double bond is not twice as strong as a carbon-carbon single bond. So while a double bond is stronger than a single bond, it's not twice the strength. The triple bond is not 3 times the strength of a single bond. A triple bond is stronger than a double bond, but it's not half as strong again or a third as strong. It's just a stronger bond. Okay, let's move on to a couple more topics now. When we are talking about carbon bonding or anything bonding to another atom, it was found out there's a concept we must look at called electronegativity. Now, electronegativity, kind of a long definition, it's the ability of an atom in a bond to attract electrons of that bond to itself. Mainly we're talking about covalent bonds here, but electronegativity is just a value given to atoms based on their ability to attract electrons to themselves. This concept was brought about by Linus Pauling, who won the Nobel Prize in 1954 for his theories of covalent bonding. Note, Pauling died in 1994. Pauling was also a very, very strong proponent of vitamin C. And I have a colleague who talked with Linus Pauling in about 1990, was at a conference with Linus Pauling. So this was 4 years before he died. He was like almost 90 years old at that point. And my colleague said, and he was as spry and mentally chipper as everything. Turns out he was in extremely good health when he died. All right, I don't know if vitamin C is his Linus Pauling said take high doses of it. I don't agree with complete high doses of vitamin C. However, make sure you get enough vitamin C in your diet. It's good for you. All right, and the best way is not with pills. Best way is with natural means via fruit and whatnot, because you get the fiber in there also. All right, so Linus Pauling was looking at atoms' ability to attract electrons to themselves, and he came up with a scale. The most electronegative element, the element that really wants electrons the most, that if you have a covalent bond between this element and any other element, it will attract the electrons in the bond to it, is fluorine. Fluorine is the most electronegative element, and Linus Pauling gave it an electronegativity value of 4. That's it, he gave it a value of 4. All right. And so if we look at the electronegativities of their other elements, according to Pauling, so you have fluorine with electronegativity value of 4, oxygen is 3.5, nitrogen is 3.0. While it's not necessary to memorize these numbers, you do need to know the trend, but it's a pretty good idea to have these numbers in your head for these guys across here, these guys going down. Fluorine value of 4, oxygen 3.5, nitrogen 3.0, carbon 2.5, hydrogen 2.2. And note, these are all our nonmetals. Our nonmetals here have electronegativity values of 2 or greater. And our metals, lithium, sodium, iron, have an electronegative value less than 2. Note, our alkali metals, lithium, sodium, potassium, have electronegativity values of less than 1. What that means is if any of these guys are in a covalent bond, they will tend to draw the electrons of that bond towards themselves. These guys will not. And note how this scale is. Electronegativity increases as you go up the table, increases left to right. So up here are the most electronegative elements. Down here are the least electronegative elements. All right, so what does that mean? Well, it means that our bonds are what we call polar. We have bond polarity. If there's electronegativity difference between the two bonded atoms, the more electronegative atoms are going to pull the electron density towards itself, pull the electrons towards itself. Well, electrons are negatively charged, so if the more electronegative atom pulls the electrons towards itself, that atom now has a partial negative charge. If it completely could pull both electrons onto itself, it would have a full negative charge, but it can't do that exactly. It can't really pull all the electrons in the bond towards itself, so it only have a partial negative charge. The other atom then, because it's missing some electron density, is going to have a partial positive charge. And we're going to call that bond now a polar bond, or a polar covalent bond. And we're going to say it has a dipole moment. For example, let's look at HCl. Hydrogen's a nonmetal. Chlorine is a nonmetal. 2 nonmetals, a covalent compound. So we can say this is a covalent bond between the chlorine and the hydrogen. Note though, chlorine has electronegative value of 3.2, hydrogen 2.2, which means chlorine is going to pull the two electrons in the covalent bond towards itself. Recall that in this covalent bond, one electron came from the chlorine, one electron came from the hydrogen. The chlorine is going to pull the electron that it started with towards itself. It's also going to pull the other electron that came from the hydrogen towards itself. Now, it cannot completely pull it onto itself. But because these two electrons are essentially spending more time, have a higher probability of being found closer to the chlorine than the hydrogen, what that means is this chlorine now has a partial negative charge, and that's how we indicate it with this delta, Greek symbol delta negative. Because it's more electronegative, pull the electrons towards itself. The hydrogen then has a partial positive charge. Note, however negative the chlorine is, the hydrogen has the same value of positive. So if this was like 0.1 negative charge, this would be 0.1 positive charge. Another way to write this dipole moment is like this. If you have HCl, you put an arrow with the arrow head, the point of the arrow at the more electronegative atom, and the feathers, if you will, you make a little plus sign at the less electronegative element. And so this is our dipole moment given the Greek symbol mu. Now here's a little math, and we are not going to be doing any of the math. From the top of the page down to the bottom of the page, I'm not going to ask you to do any of these calculations. You just need to know what they mean, what the deal is. This dipole moment is based on two properties, the charge and the distance, which means the greater the electronegativity difference, the larger the dipole moment. H is bonded to Cl here. We know that fluorine is more electronegative than chlorine, so HF would have a more polar bond. Because fluorine's more electronegative, it will pull the electrons towards itself even more, giving it more partial negative charge on a fluorine and more partial positive on the hydrogen for HF. Therefore, that would have a stronger dipole moment for greater charge. So the greater the electronegativity difference between the two atoms, the greater the dipole moment is. Also, the distance. The larger the atoms are, the greater the dipole moment. The longer it is, the longer the bond is, the greater the dipole moment. So, a few things to take care of. The dipole moment, mu, is in units of debye. 1 debye is 3.34 times 10 to the 9th third coulomb meters. We won't worry about that. The most important thing is what we just said. The greater electronegativity difference, the larger the charge is, the larger the dipole moment. The larger the atoms are, the larger R is, the larger the dipole moment. And last thing down at the bottom here is percent ionic character. All right. An ionic bond, we give it a rough value of 6.0 debye. What we're saying is if the atom, the more electronegative atom, completely took the electron away from the less electronegative atom, so we have an ionic compound such as sodium chloride. Recall NaCl is a sodium cation plus a chloride anion. This is like the extremes of polar bonds. We say that the chlorine actually took sodium's electron, so the chloride has all the electrons on it, giving it the full negative charge. The sodium has a full positive charge. This interaction of a sodium cation and chloride anion has a dipole moment of roughly 6 debye. So what we're going to say is an ionic bond has a dipole moment of roughly 6 debye. All right. And that is for a full electron charge, full plus, full minus, at a distance about 1.3 angstroms, 130 picometers, 0.13 nanometers. I like angstroms. 1.3 angstroms is the average bond distance, because I like, say, 1.3 better than 130 or 0.130. All right. We're going to define the percent ionic character as our measured dipole moment that you the dipole moment you get from your polar covalent bond divided by the dipole moment of a purely ionic, about 6 dBi times 100%. So for HCl, what we find is the measured dipole moment, if you go in and measure it, the dipole moment is about 1.2 dBi. So 1.2 dBi divided by 6 dBi times 100 means HCl has about 20% ionic character. We can say the HCl bond is 80% covalent, 80% sharing, 20% ionic, 20% this positive-negative dipole interaction. Because chlorine is more electronegative, it is pulling the electron towards itself. All right. And so when we look at this, when we do these calculations, as your book shows, what we see down here is, look at these molecules. HCl, HBr, HI. Here's our percent ionic character. Note their percent ionic character is less than 25. These guys less than 10% ionic character here. HCl about 20% ionic character. So we can safely say, yeah, those are covalent bonds. Note percent ionic character. Look at these guys: lithium fluoride, potassium fluoride, KBr, KCl, NaCl, and everything here. Note these guys, check this out. They have some covalent character. Here's 100% ionic character, so even NaCl is not 100% ionic, really. It has a little bit of covalentness to it because the sodium ion, sodium has a little electronegativity value. It does kind of want that electron. It doesn't want to completely give it up to the chlorine, so it's going to try to hold on to it just a little bit. However, we need a nice rule, and so our rule is going to be very straightforward. If our bond has greater than 50% ionic character, we're just going to call it, bam, that's an ionic bond. Greater than 50% ionic character is an ionic bond. So our normal ionic compounds, lithium iodide, lithium bromide, sodium chloride, potassium fluoride, we're going to call those are definitely ionic bonds. Note that anything with a fluoride on it tends to be more ionic because of fluorine's very large electronegativity. Note HF, though. Fluorine's a nonmetal, hydrogen's a nonmetal. We expect this to be a covalent compound. Slightly less than 50% ionic character, but it's pretty close. It's about as close as you get to being what we would call ionic without calling it ionic. It means that HF bond is extremely polar. That fluorine is pulling the two electrons in that HF bond towards itself quite a bit, but we're going to say, since it's less than 50% ionic character, it hasn't been able to really take them fully. All right. So we will end this video here and pick it up next time, looking at how to actually write Lewis structures, going through a nice way instead of the kind of convoluted, long way we've been doing it.